level system has a spin hop particle state, like up state or down state, and total number of ways you can configure, say, n particles in up state like this, right? Because you cannot distinguish among the particles which are in the down state or up state, right? So that is why n factorial by n factorial. This is the total number of particles. This n number of particles that say up state, and n minus n particles in the down state. And you cannot distinguish the particles if you interchange the particles having the same state up or down, and therefore you divide by n factorial, n minus 1 factorial, and s is the entropy, s scale and omega. You know that relation, and therefore you get this. And it tells you that the entropy is maximum at when it is n equals to n by 2. Half of the particles are up spin and half of the particles are in down spin. And therefore, if you, as you go over this, the entropy, it takes a form like this, and initially it increases as you increase the number of, say, up states or down states or whatever. At this point, you have only one configuration because all spins are up or down, whatever, whose energy is minimum. That state will be, will take, that state will take over. And therefore, suppose here all spins are up, then all spins are up means if you even exchange the particles among themselves, it will not give any new configuration. Therefore, you have a unique configuration at this position where all spins are in the up state, and then you are basically increasing the energy. That means some of the spins will be agitated and it will turn over, and therefore some of the spins will take a down position, as is a mixture of up and down positions. And eventually, if you keep on increasing the temperature at some point, or rather, if you increase the energy, because when the spins are flipping from up to down state, maybe its energy is increasing, and as you keep on increasing, finally the entropy at this point, you will find it will be a maximum, because the rate of change with number of n, number of particles in the up state. So it will take a maximum value. It will be because it will be because it is depending on omega, and omega will have a maximum value, and therefore ds dn will be 0 here, and then eventually it will take a negative form like this. Okay, so this is the maximum, but then the down spin are taking over the up states, and therefore finally here all the spins will be aligned in the opposite direction. That means in the down direction. Okay, so this is the trend, and this at this point you have some slope which is positive. This way it is negative, and that is because you get the negative temperature. The concept comes from here that it cannot go beyond this. So it is a finite energy system. It has two levels. It cannot go beyond that, and therefore the entropy takes the form like this. It is maximum when it is completely random, and then it is going to turn over the spins in the opposite direction. Finally, you have a unique state again where all the spins is having a down state. So this kind of form is happening, and this kind of stuff happens when the system has upper bound in the energy, because it has only two levels. So upper state has the bound. Okay, and in such situations you can face with the concept of negative temperature. And as I said earlier, again, to remove your misconception that if there is a 300 degree Kelvin, here it is minus 300 degree Kelvin, then they will exchange energy. Eventually they will equilibrate at this plus or minus infinite temperature. It will not go to 0. Okay, so the concept is like that. Now, so having said that about the canonical ensemble, now let us go into, or let us take an entry to grand canonical ensemble. In the grand canonical ensemble, I know for sure that you have heard that in microcanonical ensemble, you do not exchange energy, but in canonical ensemble, you do exchange energy. In grand canonical system, you do allow the particles also, in addition to change in energy, exchange of energy, you do allow the exchange of the particles. Okay, so basically it's a more open system, because this system, under the grand canonical approach system, do allow the exchange of energy and particles. and therefore you have to deal with both entropy, and also you have to deal with the chemical potential. Okay. Now that is what we have written here. We have developed a formalism of canonical ensemble and established scheme of operations for deriving various thermodynamical properties of a given physical system. In microcanonical ensemble, we consider the energy of system fixed, or more precisely within a width delta that we have already discussed elaborately. The volume and the number of particles fixed. Then we generalize the formalism to a more practical one, which we consider the energy as variable while the particle number kept fixed, that is the canonical ensemble. Next, we want to generalize it more broadly, as I said, by allowing both the energy and the number of particles to vary. This is called the grand canonical ensemble approach. So in the grand canonical ensemble, E varies, N varies, number of particles varies. And this satisfies the variables E and N and E. This statistics of variables N and E may be studied in two ways, as we did actually same approach we are going to adopt as we did for the canonical ensemble. Consider a given system A emerged in a large reservoir A prime with which it can exchange energy and particles. Okay, earlier it used to exchange only energy. Here exchange both energy and particles, and also regard the system as a member of what we may call a grand canonical ensemble. So it's a replica of systems we consider, a bunch of systems we consider, and we see the statistics of exchange of particles and energy among the members of this ensemble. These are the two approaches. And the same line of path as we did for canonical ensemble, we discussed the case of canonical ensemble. We may look at the statistics of exchange of energy and particles with reservoir, or the sharing of energy and particles among systems of ensembles. Now, first one, equilibrium between a system and a particle, a system and a particle energy system. We consider a given system A immersed in a large reservoir prime with which it can exchange energy and particles. After some time, the system will be in equilibrium with the reservoir. Then the system and the reservoir will have a common temperature T and a common chemical potential. As I said, common chemical potential, because the energy will have the energy exchange, and therefore the temperature T, it will have a common temperature T with through exchange of energy, and other one is chemical potential because it is related to the particle number of particles. And I will go fast because these prescriptions are very similar to what we have done earlier. So total energy of the combined system is A naught, total number of particles is N naught, and if the system at any instant of time is characterized by the number of particles Nr and with energy Es, then the number of particles and energy with the reservoir Nr prime and Er prime. Okay, so the number of particles and energy of the reservoir is Nr prime and Er prime. So Nr plus Nr prime is N0 constant, Er plus Er prime is 0 constant. The probability, again, same approach, same logic, the probability that the system A may be found at a state ESNR is directly proportional to the number of ways one can distribute Nr prime, Es prime in the reservoir along with the conservation of energy. Thus, the probability PRS, that is the finding a system with the state NR, in number of particles NR, and energy ES is proportional to number of ways you can distribute these energies between the reservoirs among the reservoir. And therefore this is proportional to this, as we did earlier also. Then you can write it in terms of this is the system particle, this is the system energy, and the total energy and total energy, number of particles, total energy, and this is, then you can expand them, about this total this one. Then if you take the if you expand into the Taylor series, then you get these terms, and this you designate as alpha, this is beta, minus beta, and therefore you get this form, and alpha, this is identified as minus. We have already done earlier, this is identified as minus mu by kT, where mu is the chemical potential, and this is nothing but 1 by kT. And then PRS would be is this, and ln of this is ln of you can take the ln, so ln of this equals to ln of this. So you just rewrite this form, and therefore PRS is proportional to like this. Okay, and Okay. All right. So this is and then you take the normalization factor, and this is like this. So if sum over PS, P sum over R and S, that should be one, and from therefore you have the normalization factor this, and this is called the grand canonical partition function. Okay, this is expected to be as we had in case of canonical ensemble. So this should be the grand canonical partition function. Okay. So on this probability, this is the probability that basically you see you had only this factor there, and now you have added factor this because you have allowed the particle exchange. So this is the probability that the particle could be found, the system could be found in the with the number of particles nr and with the energy es. Okay, so this is the same approach, same thing. Now, another approach is we must visualize an ensemble of eta identical systems, which of course can be labeled by 1, 2, 3 eta, mutually sharing the total energy of particles, total number of particles, say eta times n bar, and total energy eta times n e average. So this is e bar and n bar, the average energy and average number of particles per ensemble per system, and let the NRS denote the number of systems that have at any instant of time inner number of particles and ES amount of energy. So R, S could be 0, 1, 2, and so on. Then we must have the total number of systems is constant eta. Sum over RS, this would be eta. Sum of NRS, NR should be eta times average number. So this total numbers. So this okay, this is the total number of systems, and this is the total number of particles, and this is the total energy. These are the things that you can easily understand. Now we can have any set that NRS of the numbers in RS which satisfies the restrictive conditions given above. These are the conditions, restrictive conditions. You have go back and represent one of the possible modes of distribution of particles and energy among the numbers of the ensemble. So this is a the algebraic example that number of particles is 3, 4, 1. So this is one system, this is another system, this is another system. So this is the kind of ensemble where you 1, 2, 3, 4, 5, 6, 7 systems are there, and in this system you have a particles 3, this is 4, and so on. Then total number of particles is like they have 3 here, 3 here, 3, so 3. Actually, you add them 3 plus 4 plus 1 plus 3 plus 4 plus 2 plus 3, so 20. And in arrays, the number of systems having the particle in R, you see 3 particles. There are 3 systems, 3 into 3 plus 2 systems, 2 into 4 particles, 2 systems, 2 into 4. This way you can have. So these are the things. Total number of particles is 20, and that is what you. Okay, so any set NRS. Now you can understand that I'm going to look at the most probable distribution. Okay, as we did in case of canonical ensemble. Now to set this NRS, what is this? This tells you that a set where NRS eta RS number of the number eta RS which satisfies the restrictive conditions. Okay, given above represents one of the possible modes of distribution of particles and energy among the members of the ensemble. So as a exactly in a similar way, then you see you can see number of different ways that you can have. So any such mode of distribution can be realized in this different ways. And what is that? This is eta factorial by the product in RS factorial, right? Because if you have n number of systems having the same energy, same number of particles, then there is that so the exchange among themselves will not give any new state, and therefore you define this as we did earlier. Then also it could be found that if you maximize this, eventually we'll find that that most probable distribution, say in RS star, like eta, which will turn out to be like this, and that will be again the PRS, the probability distribution. Okay, so then you can write in average is nothing but sum over NR PRS, because PRS is this. So this is from the distribution. This is it. From the second approach also you get the probability, same expression, which is for the most average kind of most probable distribution, and it matches with the average value we have seen in the random walk case also. And canonical ensemble we did not derive because it is a very messy kind of calculations that we didn't go through. However, with the same logic, you could have the most probable value is the average, and that gives you the probability. So this ratio gives you the probability. And here also the same thing that then we using that probability you can get an average number of particles average sum over n or PRS, and this is this, and that can be written in this form. You can do it by yourself. Okay, you can just check minus del del alpha of this, that will give you the n average, the expression, formal expression for the average, that this one will come. Similarly, E average is this, and that could come, the same expression could be reproduced by taking the derivative with a negative sign, derivative with respect to beta on this function. Okay? So these are the formal, these are the ways of, you can, if you know this, and then probably you can just take the derivative of this and get the average energy. Okay, these are the kind of expressions you may have to use at several places if required. N-bar and E-bar, the average number of particles and average energy associated with each number of ensemble. The expectation values of the number in ENRS is identified as, of course, it will be like this because there are so many distributions possible. Then the average number of particles with R, and this is this. As eta tends to infinity, it may be shown that this, as I said earlier, as I just made a statement, when I was talking about the random walk and canonical ensemble, that this average is nothing but the most probable distribution, most probable value. So this is what it is, but we are not going to a formal proof of this. It could be again messy enough, and therefore we just take it as a statement, and which is of course true in many cases, and we have explicitly shown this in case of random walk problem. So this is equals to this, and this is the probability, right? So inference is most contribution is coming from this one, and that's why this average, they are almost equal, right? In canonical ensemble also graphically we have shown you that they are very close to each other, and if the number of systems is very large and number of particles is very large, or for a large system these are, I mean, more or less indistinguishable. They're very close to each other. Well, if you recall, the approach in canonical ensemble, we had defined a quantity which is called A in canonical ensemble. Similarly, we define a quantity which we name as Q, and later it will be said Q potential is ln of this one, this stuff. Okay, and then if you could do dq, then you can, there are four parameters you see, that alpha, ni, beta, and es, and therefore you can do del q del alpha d alpha plus del q del beta d beta, del q del nr dnr, del q del es, and des, and so on. Okay, so then you will have, there are four terms. This term, this one is zero. Now I am yet to rationalize this zero. So I ask all of you to join this venture to justify how this term is zero. But this term is zero as indicated at several places. Okay, this term is zero. Please note this one. I request you to note on this. I request you to note on this and justify why this is zero. Okay, so please do have a storm in your brain, and try to figure out or justify why this is zero. This is zero. Also, I will just proceed taking this form without, of course, explaining why this is zero. Okay, so please do participate in this venture to figure out why this term is zero. And then dq is this is zero, and therefore it only three terms are remaining, and therefore you can use this n bar as this, as we have done, we have shown you earlier here, that what are those n bar, e bar, we have shown the expression for that, so you can add them here. you can use them. So always you can use them, and then you write. Once again, you write this expression dq equals to this, so that d of q plus alpha n plus beta is basically equals to beta times um, d of q plus n alpha bar plus this. Now, can you again figure out where from these terms are coming? Beta times alpha by beta dn plus de bar minus 1 by eta and this. Hmm? No? Just can you from this to this? Can you figure out? Anyone? Pin drop silence. Nobody is speaking. Why? কেউ তো কিছু বলো।
স্যার বুঝতে পারছি না এখান
না
থেকে
স্যার
কি করে
বুঝতে
আসবে।
পারছি না।
সে কেন বুঝতে পারছো না? এটা d of this entire thing, c alpha dn n bar d alpha. So two more terms expected, right?
হুম
If you take this that side, then two more terms will be expected because you are taking d of the entire thing, right?
হুম
1 minute. না আসলে ক্লাস নিচ্ছি তো, ওটা করে চলে আসবে। ওকে, হ্যাঁ, বুঝতে পারলে?
হ্যাঁ বুঝতে পেরেছি।
আচ্ছা বুঝতে পেরেছি।
Okay, then compare the first law of thermodynamics. So then you see dq. Just look at this. Okay, my saying just reading out doesn't help. Okay, just look at it. Okay, compare this with the first law of thermodynamics. dq equals to de plus dw minus mu dn, right? তাই তো, এখন নাম্বার অফ পার্টিকেল যেহেতু এক্সচেঞ্জ আছে তখন এই টার্মটাও আসবে, রাইট?
স্যার
তাহলে ডিডব্লিউ হচ্ছে তোমার, এখানে তুমি যদি কম্পেয়ার করো তাহলে ডিডব্লিউ কোন টার্মটা হচ্ছে, এই টার্মটা হচ্ছে, রাইট?
হ্যাঁ স্যার।
Right. Okay. So this term, I think we already encountered this term earlier, right? The work done for the system to take the system to other steps, right? That we already discussed about this term earlier also in case of canonical ensemble, right? Do you remember that? Do you remember? Forgot.
ঠিক এই
হ্যাঁ স্যার।
টার্মটা
Hey, তোমরা সত্যি, you are not going with me actually. Do you
হ্যাঁ
remember
স্যার
that
এটা
the
মনে
same
আছে।
term? At least এই ছবিটা তো মনে আছে তোমার, এই জিনিসটা।
হ্যাঁ স্যার।
হ্যাঁ এই টেক্সটগুলো সেটা মনে
Okay.
আছে।
All right. Some of you remember. That's good. Well, then you how then you identify this mu as minus alpha by beta, right? Is that correct? And
হ্যাঁ এটা
you know alpha equals to minus mu by k. So
হুম,
right, there's nothing new
হ্যাঁ
here.
হ্যাঁ
So
স্যার।
again, beta dq equals to d of this one, this beta. So now you see that if you look at these expressions, okay, then you see beta dq equals to d of q plus alpha n bar plus beta e bar. This is dq, right? Beta dq equals to this, right? এটা হচ্ছে তোমার dq, right?
Yes, sir.
Now, so this beta, sometimes it is called integrating factor of heat transfer. Okay, so then you see that then you can have this d of this equals to d of s by k. How? Because dq by d of q by t. Q by t is nothing but your q by t
Entropy.
is s, right?
Hmm.
Q by t. So from there you can write this equals to d of s by k. So you connect with the entropy, and so q equals to both side derivative goes q is s by k. So these are the relations you get. So the q is, you can write in terms of this, you know, um, these parameters. Okay, t, s, mu, n, e bar, and k. Okay, actually these relations you may need, in future. Okay, for calculating something. Now look at this expression. So after going back home, or you are at home actually after the lecture, if you don't have any lecture, take rest and again, open your book and see. I have already sent you this one, okay, in your WhatsApp. So just sit down and do the calculations, okay. And q equals to ts plus mu n bar c bar by kt, and g, you know that mu n, right, gives free energy, right, and you write it this one, right, gives potential, you write this way, right, t
Yes.
minus
Yes,
s plus
sir.
b.
Yes, sir.
Okay, then this q, if I go back to the mu n bar, if you substitute it here, then you get q equals to pv by kt. Okay, q equals to pv by kt. So this expression essentially makes a link between the thermodynamics and the statistics of the corresponding grand canonical ensemble. And in this ensemble, there is an important parameter which is called fugacity, z, which is written as e to the minus alpha or e to the power mu by kt. This is called fugacity, and this will be required when we'll talk about the ideal Bose gas and ideal Fermi gas. I don't know how far I will be able to go. There, we use this fugacity. Okay, so in the grand canonical ensemble, it is related to the particle exchange because mu is there. Okay, this is called fugacity. Generally, this is the general notation, fugacity. Now, Q potential may be written in terms of the fugacity. How? Then Q is, you wrote it sum over ln of sum over the way you assumed Q is. Where is that? You assumed Q somewhere. Where is that? Here, I think. Yeah. So this one, right? This you assumed as the Q and the Q potential. Okay. So then this Q potential, you can write, if you assume z to be e to the minus alpha or e to the mu by kt, then you can write some of rs, then you separate these two things, right? Exponential e to the power exponential, this one you can write z to the power n, and e to the power minus beta es, right? And then you can write it as ln, then you sum, the two sums are now, this is over es, so you can separate the sum over es there, and then interesting, you can carry out the sum over es and then carry out the sum over nr, right, r. Then you can write sum over nr tending from 0 to whatever number, then z to the power nr, then q, because sum over, you see, sum over s e to the minus beta s is nothing but the canonical partition function, right? So you can write it in terms of canonical partition function. Okay. Okay. So this is the expression 2. You can write it, this grand canonical, I mean this potential, in terms of this ln of a function where sum over nr equals 0 to somewhere z, fugacity to the power nr q nr. This is the canonical partition function with number of particles nr. Okay. Now note that in going from 1 to 2, we have carried out sum over es, as I have already explained this. Okay. So then q equals to ln of this q zvt, where q zvt is z to the power nr q nr. This is the grand, this one is the grand canonical partition function. Okay, grand canonical partition function. I should write a canonical here also. We know q is pv by kt, so p is kt by vq, then I can write it as, and we know what is Q, what we assume, KT by V ln of this partition function, grand canonical partition function. Then you see the pressure expression is KT by V ln of this. Okay. So in case of calculation of pressure, say in case of Fermi gas or Bose gas, probably you may require this kind of expression. Okay. Now, if we write n bar, average number of particles is n, and u as the average energy, then nzvt equals to, এটা কি করে লিখলাম, nzvt equals to z del del z this. Can you justify that? আমি এটা ছোট করি, এটাকে nzvt equals to z del del z of this. এটা করা যাবে? দেখো তো একটু। So average number of particles, এটাকে এরকম করা যাবে? Let's check. বুঝতে পারছো না?
না, ঠিক কোন ইকুয়েশন
দেখছি।
আরে z টু দি পাওয়ার nr আছে, তুমি z দিয়ে যদি ডেরিভেটিভ করো nr টা চলে আসবে আর z টা কমে যাবে, সেই কমাটাকে z টা দিয়ে গুণ করে ঠিক আবার সেই আগের অবস্থায় নিয়ে চলে গেল, তাহলে nr টা বাইরে পড়ে রইলো, বাকি তো তুমি বুঝতে পারছো ই অ্যাভারেজ এন অ্যাভারেজ যেমন করে সেরকম হবে, তাই না? আর এর সঙ্গে এলএন ফেলেন আছে, নিচে চলে আসবে, তোমার এইরকম এক্সপ্রেশনটা চলে আসবে, কোথায় এন অ্যাভারেজ ই অ্যাভারেজ কোথায়, এরকম টাইপের একটা এক্সপ্রেশন চলে আসবে। এন অ্যাভারেজটা কোথায়, এইরকম কোথায় গেল, ই অ্যাভারেজ এন অ্যাভারেজ কই, অ্যাভারেজ এইরকম টাইপের একটা এক্সপ্রেশন চলে আসবে। এই যে জেড এন আর আছে না, কিউটা এটা, তো এটা তুমি ডেরিভেটিভ করলে কি হবে, এটা একটা নিচে চলে আসবে, নিচে হচ্ছে তোমার পার্টিশন ফাংশন চলে আসবে, উপরে কি আসবে, উপরে এনআরটা বেরিয়ে চলে আসবে, আর তার সঙ্গে জেডটা তুমি গুণ করে দিচ্ছ, জেডটা গুণ করলে আবার জেডটা যেমনটা তেমনই থেকে যাবে, মানে এনআরটা এক্সট্রা এসে এই সামটা হচ্ছে, হ্যাঁ, তার মানে সেটা এন অ্যাভারেজ হচ্ছে না?
হ্যাঁ, এবার বুঝতে পেরেছি।
কি বুঝতে পেরেছো সবাই?
হ্যাঁ স্যার, হ্যাঁ স্যার।
এবার সেটাই লিখছে তোমার কেটি ডেল ডেল মিউ, এটা এইভাবেও লেখা যাবে, ডেল ডেল মিউ অফ দিস কিউ মিউ ভিটি, জাস্ট চেক দিস। ওকে, আমি এটা বললাম, এটা চেক করো, আর ইউটা তুমি এইভাবে করতে পারবে, সিমিলারলি ইউ ক্যান ডু লাইক দিস। ওকে, তো ডেল ডেল বেটা মানে বুঝতেই পারছো, ডেল 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 টি ইন্টু ডেল বেটা ডেল টি করলে এরকম জিনিসই আসবে, ঠিক আছে? এটা এইভাবে লেখা যাবে। এইবার বলছে যে এলিমিনেটিং জেড বিটুইন 4 and 5, 4 and 5 একটা পি এর এক্সপ্রেশন আছে, 4 এ পি, আর এখানে আছে এন, বলছে ইফ ইউ eliminate z, then probably you will get the relation between pvt, probably the equation of state of the system. Okay, তো তোমার পার্টিকুলার প্রবলেম যদি থাকে সেখানে পি, এখানে দেখো পি, কে টি ভি জেড ভিটি, জেড আছে আর এখানেও তোমার জেড আছে, তুমি যদি দুটোর মধ্যে থেকে জেড কে এলিমিনেট করে দাও তাহলে you will get a relation between pv and t, right? So probably the equation of state of the system. Okay, again eliminating z between 5 and 6, we obtain the average energy per system u in terms of nvt, কারণ এখানেও জেড ফেড আছে, তুমি জেডটাকে যদি এদের মধ্যে এলিমিনেট করে দাও তাহলে এই দুটো ইকুয়েশনকে, এখন এইগুলো তো জেনারেল এক্সপ্রেশন, তোমার এক্সাক্ট কোনো প্রবলেম থাকলে সেই প্রবলেমে এক্সাক্ট জিনিসপত্র থাকবে, সেখান থেকে তুমি যদি এলিমিনেট করো, তখন এলিমিনেট করলে তুমি হয়তো এখান থেকে জেডটা বের করে নিলে তুমি ইউ গেট ইউ এন ইন টার্মস অফ এন এন্ড আদার স্টাফ, you get the energy in terms of nvt, other parameters. Now look at this, the Helmholtz free energy A এগুলো খুব বিচ্ছিরি টাইপের রিলেশন, বুঝলো তো? ইউ হ্যাভ টু নো ডু বাই ইয়োর সেলফ। If you look at this, the A is G minus PV equals to mu n, G is mu n minus PV. Okay, and mu also again you can write it in terms of fugacity is like this. Z is so you can write this because mu is in terms of fugacity is like this. And again PV by KT is Q. Again you can write it as a KT Q, Q. And then it can be written in this form also. কারণ এটাও এলএন টার্মসে থাকবে। You can write, just check it out that you can write this in this. You may compare with A. এটা কি ছিল? মাইনাস কেটি এলএন কিউ ছিল। এখানে কি হয়েছে? এখানে এটা ডিভাইডেড বাই জেড টু দি পাওয়ার এন, মানে সিমিলার ফর্ম কিন্তু একটু আলাদা, বিকজ দিস ইজ গ্র্যান্ড ক্যানোনিক্যাল পার্টিশন ফাংশন এন্ড দিস ক্যানোনিক্যাল পার্টিশন। এ আর হ্যাঁ মানে সিমিলার অ্যাকচুয়ালি, বিকজ জেড টু দি পাওয়ার এন জেড দিয়ে ভাগ করে দিয়েছো, ক্যানোনিক্যাল পার্টিশন ফাংশন আছে বলে, সো এন এর টার্মটা এখানে রয়ে গেছে, এটা হয়তো চলে যাবে গিয়ে তোমার if you compare this is very similar to this form. Now entropy u minus a by t তোমরা জানো, u টা এখানে তুমি পেয়ে গেছো অলরেডি, u এর ফর্মটা, where is that u form you have here. So তুমি যদি সেইগুলো বসাও আর কি, তাহলে তুমি এরকম একটা ফর্ম পাবে, সেখান থেকে তুমি s you can write in this form. Okay, del del t of tq. আচ্ছা, সেটা আমি এখানে এক্সপ্লেন করে দিয়েছি কি করে তুমি এই টার্মটা এখান থেকে পাচ্ছ। Del del t of tq n equals to, if you expand it, then first q, then t, del del q del t, del del q del n z, যার যার ফাংশন আর কি তাদের সঙ্গে ডেরিভেটিভ করে করে এই জিনিসটা হবে। So you actually you should do this, but here I have shown how to get this form. Okay, এইটা কি কেসটা এইটা কি করে হচ্ছে সেটা আমি এখানে লিখে দিয়েছি। You just do the calculations, and if even if there is some gap, try to fill the gap. Okay, now recall again the thermodynamic relation, and then you recall this, and then of course s equals to d of pv by dt, provided v and mu are constant. So this expression, then s equals to pv, you know what it is because you have the relations in terms of q, small q, capital Q. So s is del del t of s equals to k del del t, mu and n constant. So this is the expression, and this ensemble approach, this is the expression for the entropy. Now we have to demonstrate with some examples, right, how Q potential works. So this potential Q is very similar to your Helmholtz free energy in case of canonical ensemble. Okay, so now you can look at how it works. Now how about you? Are you stressed or is it's okay?
মানে কি বললেন ঠিক বুঝলাম না।
না বলছি তোমরা কি
স্যার,
স্ট্রেস
আজকে
ফিল করছো না can I proceed?
এইটুকুটাই ছেড়ে দিলে হয়, মানে অনেকগুলো তো ভিতরে ক্যালকুলেশন গুলো আছে, ওগুলো তো করতে হবে।
তাহলে তোমরা ক্যালকুলেশন গুলো করো, হ্যাঁ তোমরা যদি ক্যালকুলেশন গুলো করো তাহলে আমার একটু মানে একটু ফাস্ট যেতে পারবো আমি পরের গুলোতে, ঠিক আছে?
ওকে স্যার।
ওকে ওকে ঠিক আছে, তাহলে আমি এক্সাম্পলটা পরের দিনই শুরু করবো। ঠিক আছে বিপ্লব,
হ্যাঁ স্যার।
অ্যাটেন্ডেন্স একটু পাঠিয়ে দিও তাহলে, হ্যাঁ
হ্যাঁ হ্যাঁ
থ্যাংক ইউ।
বেশ।
পড়ো কিন্তু সবাই মিলে, কিন্তু এটা একটু পড়ো কারণ অনেকগুলো এক্সপ্রেশন ইত্যাদি আছে তো। জাস্ট ডু ইট টুডে, ওকে?